Yes, I think 4:56. Good morning. Are you there? How many of you there now? Only 4. Respond 4:56.
Yes, sir.
Okay, right. Are you able to see the screen?
Yes, sir.
Okay, good. Uh, and now only 4. What happened to remaining people?
They are joining, sir.
Okay, right. I mean, how about the previous class? Any doubts? Any queries? So let's spend 1 minute before others join. So how many different types of addresses we discussed in the previous this thing in TCP/IP communication network communication model? How many different types of addresses we discussed in the previous class? Also, you can see on the screen. Okay, what other people joined? Let me see. Okay, 468. Can you respond? How many different addresses we discussed in the previous class? Unmute and reply. 468 or 454. Nobody responding? 489. 466. Are you there, all of you?
Yes, sir.
No, you are replying, but how about others? Nobody else is replying. 453. Can you respond? 489, 466, 454.
Yes, sir.
499. Who is this? Rajeshri? Please. And all of you come with the roll numbers. Don't use your names. Rajeshri, yeah, use your number and names. You can, if you want, you can use in the brackets, not in the main. Roll number should be main. Okay. Now, let's continue our class today. So we have seen in a TCP/IP type of network communication model, we come across 4 different types of addresses. So physical address, logical address, port address, and specific address. Okay. So we have seen one example here. So there are some 4 computers connected in a LAN, and the first computer address is here we are talking about the physical address 10, and second node physical address 28, third node physical address 53, fourth node physical address 87. When 10 is communicating with 87, so at data link layer addresses are source is 10, destination is 87. So that's how these two come similarly here also. But since in the LAN, it is one half connection between source and destination. So that's why these two will directly communicate each other. That's why addresses, the source and destination will come directly. Whereas in other case, we'll see later, it will be slightly different. Let's see that. And this is physical address is 48-bit address. It is always represented as 6 bytes. Each one is 8 bits, so that way it becomes 48 bits totally. Okay, it is also called sometimes MAC address. Okay, right. Now let's see another case where these source and destination are connected through a routers on a wide area network. Here there are two routers. You see, router 1, router 2. There is one LAN 1, and the LAN 1, this system 10 is here, and this LAN is connected to one interface of this router, and another interface is connected to another LAN here. Similarly, there is one more third interface which is not in use right now. And similarly, the routers 2, if you see, this also has the 3 interfaces. So router can have any number of interfaces. So here in this case, one is connected to LAN 2, other one is connected to LAN 3. And finally, this one, where this 20, yeah. So here if you see, address 10 is connected here, whereas address of this interface is 20. Okay, so MAC address or physical address. Similarly, physical address of this interface is 99, whereas this is 44. And similarly, if you see here in this router, this interface is 33, this is 66, this is 55. And here this address is 95. Now, when there is a communication from 10 to 95, it goes in halves here, because first it reaches the router, interface 20, from there, and through interface 99, it comes to interface 33 of router 2. From there to interface 66 of router 2 reaches 95. Now that's why you see this one here addresses, this is the source 10, 20, this is the destination. At data link layer and physical layer, I'm talking about data link layer and physical layer, and above that is a different. Okay, so now it comes to 2010, and whereas when it is going next hop, it becomes 99 is the source and 33 is the destination. Similarly, when it goes in third hop, 63 is the source, 95 is destination. So that's how these addresses keep changing for every hop. But same thing if you look at network layer, this is system A and this is system B. Finally, we are communicating from this system to this system. That means A is source, B is destination. This two remains same throughout the link. So we see here at this interface, at network layer is A and P only. Similarly, here also it is A and P. Here also it is A and P only. Source and destination. Those things do not change. Whereas at data link layer and physical layer, these addresses keep changing for every hop. So that's a difference. Now let's see the next one. We said at transport layer, we said it is process to process communications. For that, let us see the example here. Let's see there is a computer A here, computer B, as we have seen, and remaining routers here for simplicity purpose, they are all merged into the network here. Now A, B, C are processes at system A or node A, and J and K process at system B or node B. Sorry, not this receiver and receiver. Now is it clear or any? All of you are able to follow me? Yes, 4A1, can you reply? 4A1.
Sir.
Are you able to follow me?
Yes, sir.
Okay, good. Yeah. Now, so we are talking about addressing mechanism at transport layer. Here, A is address, node address, whereas A, B, C are process addresses, port numbers. We call it a port or process number, right? J and K is ports here. Similarly, P is system address. And here, when it comes to application layer and then transport layer, it comes. Transport layer deals with process, right? Process to process communication. Now, process A is trying to communicate process J. Process A is located at node A, and whereas process J is located at node P. So that's why A is communicating to J. A is the source address, source port, J is destination port. So when it comes to network layer, it gives node to node communication, right? Host to host. Host address here is A, and host address here is P. That's why A is the source, P is host. Okay. These A and P are host numbers, addresses, whereas A and J are process addresses. Okay. Now coming to data link layer. Here is a hop by hop. Here, assuming that they are directly connected here, case 2 gives source and destination address of first hop, next hop, third hop, fourth hop, like that it goes. This is to use the last hop of this one. So here this keeps changing for 8 hop, whereas AP, that is a host address, and AJ process address remains same throughout the link. Whatever may be the number of intermediate hops in this network. So that's what you have to understand. Now physical address will change from hop to hop, but logical address usually remains same. This is what we see in that. This logical address is nothing but this capital A, capital P, that is node address. Okay. Small a and small j are process addresses or port addresses. Now, this port address is a 16-bit value, and normally it is given as a, like this one, this decimal value. It is represented in the decimal value 753. Some number. This is one of the port address. So it can vary from, that means 0 to 65,355 or so. So that means number. So it is a 2 power 16, that value. So physical address change from hop to hop, logical address and port address usually remains same. Okay. Whereas the logical address is, there are two versions, version 4 and version 6. Version 4 is 32-bit address, version 6 is 128-bit address. That also we will see as we go into remaining the chapters in detail. Okay. So MAC address is, physical address is 48-bit address and keep changing for every hop. And logical address is either 32-bit or 128-bit, one of them, and remains same from source to destination throughout the link. And similarly, port address is 16-bit value, so it also remains same throughout the link. Okay. Now coming to, there are two more terms here: encapsulation and decapsulation. Encapsulation is nothing but, if you see here, back. Let me explain. Yes, this is it. So what we discuss here, when message is coming and it is divided into small parts, and each part is dealt at a time, and that part of the message is taken. For that we are adding header, and trailer also is there, but it is hidden into the H7 header itself. So that means the data is embedded along, in between header and trailer. Okay, this process, embedding or putting the message between header and trailer, is known as encapsulation. This encapsulation is done at every layer. So if you come to the presentation layer, this entire thing is taken as a message, and this is put in between header and trailer, assuming that there is a header here. Similarly, session layer, and then transport layer, network layer, data link layer, physical layer. Every place this encapsulation takes place. Similarly, at the receiving end, decapsulation takes place. Here, when it comes there, it removes this header and trailer and hand out this only the message part to the upper layer, that is data link layer. This removes these two parts and remain only forwards this D2 to this one. Then this removes S3 and then forwards to this transport layer. Transport layer removes this forwards to session layer. Session layer this removes this and forwards to presentation. Presentation removes this and then forwards to the application removes this one and forward. This removing of head and trailer is and extracting actual message from each layer is known as decapsulation. Whereas inserting the message between head and trailer is known as encapsulation. This is decapsulation. So sender side we always do encapsulation at every layer, and the receiver side we do decapsulation at every layer. And next one is another point which we have to discuss is
Sorry.
yeah, tell me.
Sir.
Yeah, yeah, tell me. Can you come back again? What is it? What is the problem? Hello.
Your voice is not audible, sir.
Voice is not audible.
Yeah.
Okay. How about others? Are you able to hear my voice? Yes, respond. All of you. Hello.
Yes, sir.
Yes, sir.
Okay, I think that student, please, check at your end because others are able to listen to my voice. Please check at your end. And now, next point what we come across is multiplication and demultiplication. So if you see at several layers, again we take an example and see. Yeah. See, at many layers, these things are coming from many processes may keep coming. Like if you see at the application layer, processor that different process may generate data messages. So those messages will go through the same link as long as the destination also at the same node. Okay, or at least a part of the link, though the destinations may be different for different processes, but still they travel in a common route for at least for some distance. So in that route, they can be multiplexed and sent. Okay, so similarly, the receiving end you can demultiplex it. So that's why at all these layers, because data which is coming may be related to multiple applications and multiple processes, so they always multiplex and sent through the link. At receiving end, they will demultiplex and hand out to the corresponding process. So that's what these addresses and multiplexing and demultiplexing. Okay, so these are things we do at network model. Till now, if you see whatever we discussed, let us make a few questions. One or two questions. Let's see how many of you followed it. Okay. Yeah. Now this answer. Internet model consists of dash number of layers. Can you answer this question?
5 layers, sir.
Okay. Good. And another question. Dash layer is the layer closest to the transmission medium, which is closest to the transmission medium. Medium is actual link or channel. Which is the closest out of these four?
Physical layer.
Yeah. Yeah, above that data link layer, network layer, transport layer, they come on. Okay, closest is this one. Okay, now the data pack moves from the upper layer to the lower layers. Headers are when they are traveling from upper layer to lower layers. When what happens to the header? Header is added or removed or rechanged, rearranged or modified. What is that done? When it is traveling from
Added.
added. Okay, but I expect answers from other students also, not the same student all the time. Okay, right? Okay. Now let's go to the next part of it. So here we are going to discuss when you are sending the data, what happens, how do we transmit data, and it is more related to physical layer. Okay, so as you know, at physical layer, what do? We convert these zeros and ones, data, binary data into signals, right? Okay, so there are two things. One is data, another one is signal. So data is converted into signal, and that signal is carried over the link, this carrier. Okay, and the distance end again, these signals are converted to actual data given. This data, so that means there are data element and signal element. There are two things. So but both can be either digital or analog. So that way you will have analog data element and analog signal element. Similarly, analog data element and digital data, signal element. Like that, the four combinations are possible anyway. Those things you can imagine. But you see, actually, data can come in analog or digital. But we convert for digital because all computers comfortable to handling a digital data, we convert, and processing is done using in a digital form. But while transmitting it in the medium, it is always as a signal, analog form travels. So that's why we need to understand both of them. And some preliminary information, I think all of you have it. What is the difference between digital and analog signal? And then modulation techniques, periodic, non-periodic, those things. But let's review it quickly and go into the system. Data can be analog or digital. Analog data are continuous and they take continuous values. Digital data have discrete states and take discrete values. Okay. So these signals can be analog or digital. Analog signals can have an infinite number of values in a range. Digital signals can have only a limited number of values. This I think it and representation is known to all of you. And in data communication, we commonly use the periodic analog signals and non-periodic digital signals. This is what we are going to use in data communication. Okay. Now, when it comes to periodic analog signals, can be classified as a simple composite. A simple periodic analog signal is a sine wave. Okay. Cannot be decomposed into the simplest signal. A composite periodic analog signal is composed of multiple sine waves. When you say composite, this is simple sine wave, right? And when you have these things are known to you, that's why I'm not showing you. So this frequency and time domains also is familiar to you, whereas the time domain signal variation is shown here, and frequency domain as a single bar we show it this one. Okay, frequency element. Yeah. If there is a composite signal is having multiple continuous signal. So they can be divided into or separated using Fourier analysis. This also is known to you, right? So each sine wave, that component can be having a different frequency, different amplitude, and different phases. When all these things are combined, then you will get a composite signal. Okay. If a composite signal is periodic, the decomposition gives a series of signals with a discrete frequency. This, let's see, understand it. This one. If this is a composite signal, so if this is using the Fourier analysis, if you decompose, then you will get like this. There are discrete frequencies but continuous frequencies. So this is one frequency sine wave, this is another frequency sine wave, this is another frequency sine wave. In a time domain. Same thing if you when you represent in a frequency domain. So F, 3F, 5 of these are harmonics. This one, right? That's how it comes. That is related to periodic composite signal. Okay. If the composite signal is non-periodic, please remember that. The decomposition gives a combination of sine waves with continuous frequencies. Okay, this is the difference. Now look at composite signal, which is non-periodic. When you decompose using the Fourier analysis, it gives number of frequencies, continuous frequencies. Okay, this range of frequencies. Okay. So then normally, whatever data we are transferring is always non-periodic. Very rarely they are periodic. So that's why this becomes very, very important. So the bandwidth of composite signal is difference between highest and the lowest frequencies contained in that signal. So bandwidth of this signal is, that means what is the lowest frequency and what is the highest frequency. Between these two, that is, we call it bandwidth of that signal in the frequency domain. Now you can see bandwidth of periodic and non-periodic signal. You can say periodic, non-periodic, because it is a continuous frequency ranges. So that means you have all the frequency components inside it, whereas in a periodic you have only discrete frequencies, not continuous frequencies. That's bandwidth. Okay. Now these are the examples. You see, if a periodic signal is decomposed into 5 sine waves with the frequencies 100, 100, 500, 700, and 900. So the bandwidth is between this one highest frequency and lowest frequency. Right? So it's 800. So, but when you represent the frequencies, it gives only the 5 bars: 100, 300, 500, 700, and 900. Like this. So here is another example here. Okay. And non-periodic, if you see, this is one. Yeah, 200 kilohertz and 140 kilohertz between that. So it will have continuous signal. You can see that here. You see, 40 kilohertz to 240 kilohertz is a continuous. It will have, of course, some peak, and the signal strength also keeps varying from frequency to frequency. Okay. Non-periodic composite signal is a signal propagated by an EM wave. Okay, EM wave is shown here. These examples, let us ignore for some time and go to the next one. Digital signals. So digital signals, when you are transferring it, number of bits you are sending it, bit rate, bit length, and then digital signal as a composite analog signal application. These are things we go into this. So when you take the signal, the digital signal, it will have multiple levels. Okay, maybe here it is having only 2 layers. Here it is levels, whereas here it has 4 levels. Okay, so to present these levels, we use again combination of bits based on that. So in this case, because there is only 2 levels, so 1 bit is enough, either 0 or 1. Whereas here there are 4 levels, we need 2 bits because there are 4 different combinations are there. Similarly, if it is 8 levels, then you need 3 bits. So that's what I mean given in this example also. You can look at this. The digital signal has the 8 levels. How many bits are needed per level? Okay. So using 3 bits, you can represent. If it is less than 3, you will not be able to represent all the levels. That's a difference problem. Okay. And when you are converting into number of bits required, fraction is not always not taken, and it is taken next highest binary level. That means we use here already binary numbers only. So that means it always number of levels goes by. Yeah, it's going out of time. I will take just another 5 minutes after this. Please rejoin again if it is disconnected, and then we close it. Okay, so it's always taken as a power of 2. So in this example, when you are calculating, it is coming as a number of levels bits required as a 3.17, but 17 is not possible. Highest next is 4 bits. Okay, that means, yeah, 4 bits can be taken. So that means 16 levels. So assume we need to download text document at the rate of 100 pages per minute. What is the required bit rate of channel? We can use that one. 100 pages we are tracking. Each page assuming 24 lines and 80 characters. That means 24 multiplied by 8. That many characters are there in each page, and there will be 100 pages. So each character is represented with 8 bits. So total number of bits coming to transmit 100 pages is this much. 1,636 bits. So that many we have to transmit per second. So that is the rate we need. Our channel should support it. Okay. So similarly, we can transmit for calculate for different things. We'll go to this. Yeah. Yeah. This we have, of course, we have seen this one. Continuous periodic digital signal and aperiodic digital signals, how they can be represented in the frequency domain. Now, assume that this digital data has to travel through the medium. So that means when you transfer this thing, you look back. So when the one bit of information, which is represented as a pulse, is transmitted, it needs a continuous this thing. It needs a large bandwidth right from 0. That means the channel should act as low pass filter. What is low pass? Low pass filter starts from 0 and allows till certain frequency. So that we call it a low pass signal. So it acts as a low pass signal. So this signal is a composite analog signal with an infinite bandwidth. So strictly speaking, or theoretically, it should have infinite bandwidth. Then only you will get the at the receiving end you can reconvert back to original shape. Okay. So these channels can have a different bandwidth, in larger bandwidth and then smaller bandwidth. And then when bandwidth is not infinite, channel bandwidth is not infinite, what happens? Okay, if it is infinite, we can get back original shape. If it is not infinite, that means some frequency components are missed at the receiving end, right? They are filtered out by the channel. So that's why the shape of this signal keeps changes. Okay, to retain the original signal, you should have infinite bandwidth, but infinite bandwidth channel getting is very rarely possible. So that's why always, if we have to think about practical channels, so they'll always have a limited bandwidth. So that's why you will not be able to receive original listening, but nearby, closest to the original shape can be possible. Baseband transmission of digital signal that preserves the shape of the digital signal is possible only if we have low pass channel with an infinite or very wide bandwidth. Okay. Now, let's say when you are sending, what is the bandwidth required for when you are sending at a particular rate? Assume that we are sending at a bit rate of n. You need to represent that. That depends on what is the data bits are represented. When you take it as a n equal to 2, that means you have 4 combinations. So 0, 0, 0, 1, 1, 0, and 1, 1. Similarly, if you take 3 bits, it will have 0, 0, 0, and it goes on up to 1, 1, 1. So when it is traveling, the highest frequency happens when the digits are, every digit is changed every time. That means say 0, 1, 0 or 1, 0, 1, like that. Alternatively, if we keep changing, then the signal also keeps changing alternatively. So that is the highest frequency. That means how much is there is 1 by 2. So that means highest frequency required is n by 2. And of course, when remaining combination of this pattern may not vary at that rate. Let's say 0, 0, 1. So this is 0, 0, 1, and this is only 1 here. Here 0, 0, 1. So this, in fact, if you calculate, becomes n by 4 frequency. Whereas here 0, 1, 0 or 1, 0, 1 fit here. It becomes for every 2 it is changing the cycle. That means you need n by 2 is the highest frequency, and below that, yes, n by 4, n by 8, all these things are less than that. So that's how you get for any data rate, what is the bandwidth required, minimum bandwidth required is n by 2. That's all. Rough calculations. Okay. Secondly, digital signal with first 3 harmonics. So when you add harmonics also, it makes much smoother, right? But when you add harmonics, you need bandwidth will get increased, say n by 2, and the remaining harmonics when you add, the bandwidth becomes larger. but shape of the signal becomes improved. The baseband transmission, the required bandwidth is proportional to the bit rate. If we need to send bits faster, we need more bandwidth. Okay, let's see, as n increases, suppose when n by 2 also increases. Examples are here. So n equal to 1 kilobits per second bit rate, and then harmonics is 1, then we need 500 kilobits, that means n by 2, right? Okay. And this 1000 bits, 1024 bits second we are changing, so that means half of that is 500. Only if it is 10 kilobits, this is 5 kilobits. 5 kilobits. If it is 100 kilobits, then we will get 50 kilobits. Then when you add first and second harmonic also, then it multiplies bandwidth requirement 1.5, 115, and 3. Then more harmonic 1, 3, and 5 also increases, then much larger bandwidth is required. So as the number of harmonics required, of course, shape of this received signal will be much better, close to the original one, but bandwidth requirement will be very large. Okay. Now, what is required? Okay, these things, so we will not go to that. It's the same example, we have seen that. And normally the channels, we use band pass channels, right? So when you're using band pass channels, but if you want to distill it as it is, if you want to send it, you need the medium to act as a low pass filter. Okay, but when you have a band pass channel, then you need to convert into analog signal using this modulation technique, where they can be put over a carrier, and that can come between two frequencies. So that can be passed through band pass channel. So if available channel is a band pass channel, we cannot send the digital signal directly to the channel. We need to convert digital signal to analog signal before transfer. This is done using certain modulation technique. Let's solve full signal, digital converter, then we put into this and channel send through band pass signal. Okay, at the receiving end, we do the reverse process. Okay. Examples are given here, and this process which is converting analog to digital or digital to analog is called modem device. Okay, so transmission impairments. While you are transferring through a medium, so the signal suffers some amount of this thing, are subjected to certain issues. Those are called impairments. Okay, signal travel through the transmission media which are not perfect. The imperfection causes signal impairments. This means that the signal at the beginning of the medium is not the same as the signal at the end of the medium. So what is sent is not what is received. There are three causes of impairments. One is attenuation, distortion, and noise. Okay, so let's see these one by one what these are. So impairments, attenuation, distortion, noise. So attenuation is getting reduced signal strength. Signal strength getting reduced. If we are sending the data from point 1 to point 2, okay, it gets, because of transmission medium absorbs some signal, so it gets reduced in the strength. Okay, or using the amplifier, you can always amplify the signal strength. It can be, when it is reducing, we call it attenuated. When it is improved by amplifier, then we call it amplified signal. Okay. Okay, these amplification and attenuation is normally represented as by a unit called decibel. This is also familiar to you. So when power is, or when it is transmitting from one point to another point, if it is reduced to half, then we call it attenuation is, loss of power is 3 dB, and it's 3 dB. So it is always measured as